Welcome Franken friends, I'm Greg Smith, aka Dr. Frankentosh, and today I have Simplified VGA for the Raspberry Pi Pico. Last time I delivered Simplified HDMI, and now I'm going to give you 640 by 480 by 8 bits of graphics with up to 32,000 colors, right after this. Welcome back. As usual, please don't like this video, don't subscribe to my channel, don't click up there or down there. Your time is precious. Please use it wisely, and thank you so much for spending part of it with me. And now, let's get started. As before with my simplified HDMI, I have some design goals. First thing is that I want it to be a simple interface that a C programmer can access. I want to run on a single core, specifically Core 1. I want to have multiple graphics modes from 320 by 240 up to 640 by 480 and everything in between, with up to 8 bits of color on a 32,000 color palette, and finally text modes if that's possible. So for today's demo, we're going to be looking mainly at my Screensaver example. At the top of the program, you'll see that there's a height and width, the number of bits, the number of colors are then computed from the bits, whether or not we're using double buffering, whether or not we're using interlace, and finally whether or not we're synchronizing with the Core 1 processor. The actual program itself is pretty straightforward, not much to it. We create a color palette. We initialize GVga, which is the VGA library. If it turns an error, we throw an error screen. Otherwise, we set the palette to whatever this palette is up here. We start the VGA engine on Core 1, and then we draw a box, initialize the screensaver, and then iterate forever. And we do some statistics in here. We gather the current time, we see how long a frame has been running, and then we actually do some nerd statistics on the graphics. And in the middle here, we update the screensaver. I'm not going to go into the details of the screensaver. I did that in the last video, and of course you've seen this sort of screensaver before. So before we get started, what you're going to see is me sharing with you how to create the different graphics modes, 320 by 240, 640 by 480, and the challenges that I had as I went along and how I solved them. The three big solutions to the timing issues were synchronization, which we'll talk about as being synchronizing Core 0 with Core 1, double buffering, the ability to use a foreground and background bit plane so that we aren't drawing on the memory at the same time as we're displaying it. And finally, interlaced graphics, where we're showing half the scan lines on the even frame and the other half on the odd frame. So let's get started. So this is 320 by 240 pixels with only 1 bit per pixel. And as you can see, the display is not stable. We're getting what's called tearing in the middle, where we're not able to see all of the graphics. And this is because the frame buffer is being drawn on at the same time that it's being displayed. And when this happens, there's interference. We're actually clearing the frame buffer and then drawing our lines and also some statistics in the middle. And so we can't see everything at the same time because the frame buffer is being interrupted while it's being displayed. Now, one way to fix this is to synchronize so that we wait until the frame buffer is done being drawn, and then we update the frame buffer with our code in Core 0. So Core 1 is trying to display the frame buffer while Core 0 is trying to draw on it. So back in our code again, we have our screen width set to 320 by screen height of 240, a single bit of pixels, and then down here we're going to turn synchronization on. So when we look at the main loop, you can see here that at the top of the loop we check to see if sync is turned on, and if so, we call GVga sync. And what this does is it waits for Core 1 to finish displaying our frame buffer, and when it's done with the frame buffer, it releases it back to Core 0, where we can now do our screensaver graphics and display our nerd statistics. And then when this is done, it'll go back to the top. It waits until the frame buffer is acquired, and then it waits again until the frame buffer is released, and then we do it all over again. So now that we've synchronized the display, you can see that the display is now stable. We've got 320 by 240 by 1 bit, and we're doing 60 frames per second. And you can see here that the milliseconds per frame is about 16. So this is what you want to see, and At this point, we're only drawing 16 lines at a time, and so this is all working pretty well. So let's step up to 2 bits per pixel. As you can see, the frame rate is still below 60, which is great. We're still displaying our raster lines or our bouncing lines in less than 17 milliseconds. Let's step up to 4 bits per pixel. So now we're getting more colors, 16 colors from a palette of 32,000, and we're still drawing in less than 17 milliseconds. And let's step up to 8 bits per pixel. So everything is working really well. We've got 8 bits per pixel, we've got 256 colors from a palette of 32,000, and we're using 76,800 bytes of memory in order to do this. So the next step now is to see if we can't do more work. Let's see if we can display more lines while we're displaying all these pixels. So I'm going to go from 16 lines, so you can see them dancing around, to 256. So what you may not notice here is that our nerd statistics are no longer showing in the middle of the screen. And that's because it takes longer to draw this display than it does to display it. And so there's not enough time for Core 0 to finish drawing all of the information before Core 1 takes over and draws the screen again. So we can fix this by going into what's called double buffer mode. I'll talk about double buffering a little bit later. Now let's go to 640 by 480. So back in our code, we'll update the screen width and the screen height to 640 by 480 and 1 bit. And then down here in the initialization, you can see the GVga init is called with the width, the height, the number of bits, and we'll talk about double buffering and interlacing mode presently. Okay, so this is 640 by 480 mode with a single bit pixel. We're doing 256 lines, and as you can see, the display is flickering. We're not getting the entire frame buffer being displayed because our nerd statistics are not showing up. And that's because Core 0 doesn't have time to redraw the entire display before Core 1 takes over and starts drawing it again. And again, we can fix this by turning on synchronization. So now we're going to wait for Core 1 to finish displaying the buffer, and we still have trouble displaying all of these pixels in the amount of time that it takes Core 1 to draw it. So I'm going to drop back a bit, and I'm going to turn down the number of lines that we're drawing back down to 16 to give Core 0 a little more time to draw so we aren't being as CPU intensive. Okay, so we're using synchronization. We're drawing our frame in the amount of time that it's allotted. You may notice that at the very top we're not seeing the entire first line, and that's because we are running a little bit close to 60 frames per second in drawing this display. So let's step up to the next level, which is 640 by 480 by 2. So we're at 640 by 480 by 2 pixels. And when you see this blue block and black block on the screen together, it's telling you that the VGA engine can't keep up. And so we've run out of buffers. And the way to fix this is to display only half as many pixels. And we'll do that with a technique called interlace. We'll display the even lines on the even frames and the odd lines on the odd frames. And in between, we'll show the background color. So let's take a look at how to turn on interlace. So again, at the top of our code, we're at 640 by 480 by 2, and I'm going to turn on interlace. So we'll just set this to true. And down below in our initialization section, you can see here that there's a flag for turning on interlace. Let's see what that looks like. Okay, so we're now at 640 by 480 by 2 pixels. As you can see, the display is now working. We're not seeing any more of the blue and black boxes at the bottom, but the display is not coherent, right? We're drawing over the frame buffer at the same time as we're displaying it. So I'm going to turn on synchronization to see if we can fix that. And now we have a stable display. So once again, what we've done is we've turned on interlace so that every other line is being drawn on every other frame. So, but you may still see some artifacts here. You may see that our dashed lines don't look quite right. And that's because we're still outside the range of the ability of Core 0 to draw all of the lines before we go back to Core 1. So let's go ahead and step up to 4 bits per pixel. And now we have a full display with 16 colors from a palette of 32,000, but we've used up 154,000 bytes of memory. So If we try to go to 8 bits per pixel, it's going to double the range of the memory. We won't be able to load that frame buffer. It's larger than our memory. Now I want to demonstrate the artifacting that we're having by increasing the number of lines that we're drawing. This is going to exacerbate the amount of processing that we have to do in Core 0 and really show off how bad this artifacting is, and then I'll show you how to fix it. Okay, so we've got a lot more going on, and you can see a lot more artifacting here, a lot more fragmented lines, a lot more flickering, and again, we're not able to show the nerd statistics. Okay, so at this point, we've got 320 by 240 by 4 bits per pixel, and we've got synchronization turned on, and still we have problems with a display that is not coherent. And one way to fix this, if you look in the middle, you can see our nerd statistics are flickering, and our other lines appear to be flickering as well. So what we can do is what's called double buffering. We're going to create another frame of memory that we draw on while the first frame, the show frame, is being displayed by Core 1. So while Core 1 is displaying one frame of memory, Core 0 will be drawing on the other one. So there'll be no interference between the two cores. And then when we're done drawing, we'll swap. We'll put the drawn frame in the foreground, and that will be our display memory or show memory, and our memory that we're drawing on will go into the background. So these two frames will just swap back and forth. So let's turn on double buffering and see that in play. Back in the code, we've got our screen width and screen height set to 320 by 240. We've got 4 bits of color, and we're going to set double buffering to true. And then down here in the initialization section, you can see here that double buffering is one of the parameters that's passed in. All right, so I hope you can see now that our frame is much more coherent. There's not any flickering. We don't have lines that we're showing and flickering on and off. Because we are now drawing, and you can see that we're also up to 32 frames per second, we're drawing on the display in the background with Core 0 while Core 1 is showing the display on another frame. And then at the end of our drawing sequence, we swap the two frames so that the one being displayed is the one we were just drawing on, and the one that we're drawing on was previously being displayed. So and you may also notice that we're using 77,000 bytes of memory, and that's because we have two frame buffers, one for display and one for drawing. Now let's see if we can get this working at 640 by 480. Okay, so here we are at 640 by 480 by 4 bits, and as you can see, we've got the blue and black display, which indicates that we've run out of buffer space. The Core 1 cannot display the frame buffer, in enough time. So we're going to turn on interlace, and mind you, we have synchronization turned on as well. Okay, and so our display is now working again, but we have a lot of flicker. Not all the nerd statistics in the middle are not being displayed, so we need to turn on double buffering. However, the problem is that we're already using over 150,000 bytes of memory, and if we double the amount of memory we're using, we're going to overflow the Pico 1. So we're going to have to drop down to only 2 bits per pixel, and I'll turn on double buffering, as well as interlace and synchronization. And now our display is fully coherent. We're only getting 21 frames per second because we're doing so much work here, drawing 2 bits per pixel on a plane of 640 by 480, but it's a completely clear and coherent display. So now we want to demonstrate what I would call mixed mode graphic resolutions. So normally we do 320 by 240 or a multiple of that, 640 by 480. But what if we said only 200 pixels here? So that would cause the VGA engine to have too few lines to scan. So what we do is we pad the top and the bottom with enough pixels to create 240 total. The other thing that we do, if we say go past the median, so normally 240 is what we would put here, and what if we went to 360? In this case, we have more pixels than we can show in a 240 line frame. So what we do instead is we cut the pixel width in half vertically, and we show 480 pixels on the screen, and then we pad at the top and the bottom so that 360 pixels are in the middle, and then we have 40 at the top and at the bottom. Also, I want to show you how you can set the color that you use for the padding at the top and the bottom. So you would call GVga set border colors, and you would specify your GVga context, and then the color that you want the top, bottom, left, and right. Left and right padding has not been specified yet, but you can set the top to GVga red and the bottom to GVga green. And so when there's a padding needed at the top and the bottom, you can set the border colors to whatever you want. They default to the background color that you specify in the palette. So what I'm showing here is a mixed resolution. We've got 320 by 200 pixels. The red area at the top is a pad, and there's padding at the bottom. I've set the padding for the top and the bottom to red and green just to demonstrate that we have padding there. But normally what you would do is you'd set the padding to the same as the background color, so you wouldn't recognize that. Also notice that we're getting quite the high frame rate, and that's mainly because we're only drawing 16 trace lines with the Screensaver. So if I up this to 256, you'll see that it should go down. So again, this is 320 by 200 by 8 pixels. And also you should notice that the lines, the scan lines are doubled, so that they're thicker vertically. Yeah, there we go. So now we're down to just 80. So this is pretty good. And one of the other things is we're getting a higher frame rate because we're drawing fewer pixels. We only have 200 vertical pixels. So let's go up to 360 vertical pixels. So now we have 320 by 360 by 4. Notice the frame rate's gone down by a half. That's because even though the display looks the same size, we have twice as many pixels vertically. And that means that we have more pixels to draw when we're drawing our background. 320 by 480. Okay, so using double buffering with interlace turned on, we have a very clear display. 320 by 240, 320 by 480 by 4 pixels. So now let's try 640 by 240. Okay, so we have a nice frame rate of 46 frames per second at 640 by 240 by 4 pixels with double buffering and synchronization turned on, as well as interlace because we are doing 640 by 240. So let's go 642 by 360. Okay, we're out of memory. So let's go 640 by 360 by 2. So this final demo shows that we've got 640 by 360 by 2 pixels. We've turned on double buffering, interlace, and turned off sync to get a higher frame rate. And this is showing that we can modulate the amount of memory that we use by changing the vertical dimension. And when the vertical dimension demands it, it will use thinner pixels and put padding at the top and at the bottom. So our final demo is for graphics generated text. This is not a text mode. I have imported the Commodore 64 character generator so that you can draw text on the screen. It is not the most efficient way to draw text. It's implemented in the GFX library rather than in the VGA library itself. So there is a way to draw it, and this demo also shows off the fact that with single-bit graphics we can color or change the palette in real time and will cause a flashing of pixels on the screen. So we now have a coherent package for doing VGA graphics on the Raspberry Pi Pico 1. So we did have some timing issues. The first one being the synchronization. So we resolved some of our fragmentation with the sync command. Another one was running out of CPU time on Core 1, which we resolved with interlace. And then finally, we had some trouble with creating a coherent display, which we resolved by using more memory and double buffering. So another thing is that this was all done on the Pico 1, which only has 256K of RAM and runs at 133 megahertz. I just got my Pico 2 in the mail from Adafruit, so a future project will be to run this again on Pico 2 and see if we get better performance, both because we have more memory and a faster processor. So as always, thank you so much for spending time with me. I'm looking forward to seeing you on the next Dr. Frankentosh.